So let us start. Today we are going to start a new topic called stable and unstable equilibrium. Stability of equilibrium. So till now actually we are concerned about only the equilibrium of forces, right? So now actually we are going a little step ahead, that is stability of equilibrium, right? So we have derived all the conditions in case of coplanar forces and in case of 3D forces. So whether the system is under equilibrium or not, right? Now actually we know that the system is under equilibrium, but the next question comes, that is whether the equilibrium is stable or not, what it essentially means for us. Suppose if I take this particular scenario, let us say there is one base like this, and then actually, so I have given a rod, and this rod is actually, so like this actually, so by balance actually I tried putting in this particular manner. Now actually it is under balance condition, and then actually I left it like this. So now actually on this rod, the weight that is acting downwards and the normal reaction that is acting upwards. So the system is under equilibrium condition because R is equal to W, hence the system is under equilibrium condition, right? So these two forces are balancing out, and then these two forces, it will make this particular body under equilibrium condition. Now suppose by an external force, if I just push these two like this, so I just push it like this. Now actually, will it be still under equilibrium condition, or actually it will fall down? Suppose if I push a little like this, then actually, so it will try to fall down like this. Correct or not? Right? Yes or no? So if I give a little displacement to this one, it will fall down like this. So this kind of scenario we call as unstable equilibrium. Unstable equilibrium. So here actually, initially the system is under equilibrium condition, but a little displacement if you give it, it is making unstable equilibrium. That means it will fall down, it will go out of equilibrium condition. So it goes giving a little displacement. Will move the system to non-equilibrium case. Is called unstable equilibrium. This is unstable equilibrium. So I will give you one more case. So suppose there is a nail here, and then actually, so there is a wooden block that got supported by this particular nail. Now actually it was under balance condition at this particular scenario, let us say. So that means through balance actually I could able to manage that actually this is standing on the nail like this. Now if I give a little displacement to this one, automatically so it will fall down to like this. So this is after the movement, right? So it will fall down like this. So initially the system is under equilibrium condition, but if you give a little displacement, it will fall down to this scenario. So this is what is called unstable equilibrium. Suppose if I take the other case, so the same thing, the nail is on the top. So this is how the wooden block is supported by the nail. And then you have given a little displacement like this. Now what happens? If I give a little displacement in this direction, what happens to this wooden block? It will come back automatically. So it will come back to its initial equilibrium condition. And the equilibrium is called as stable equilibrium. So this is stable equilibrium and this is unstable equilibrium. I hope you got an idea what is a stable equilibrium and unstable equilibrium. So in the previous class what we have discussed is the principle of virtual work that is applicable for this one. So principle of virtual work applicable for stable equilibrium bodies or stable equilibrium forces. Right? So the principle of virtual work will not be applicable under unstable equilibrium because so the previous version, that is the principle of virtual work, what it says is if you give a little displacement, you have done some work, it will be coming back to its original position. That means it is releasing the energy that it got acquired. But here in this case, if you give a little displacement, it will fall down like this. That means it is moving the body away from there. So it won't come back. Obviously the work done is more, right? So that's why it is releasing the energy in the form of work. So this is unstable equilibrium. Hence the principle of virtual work will not be applicable here. So here dW whatever you have given it will be 0, but dW is not equal to 0. It will keep on move further. So the energy is keep on release so that it will fall down like this. Got it? So this is the principle of virtual work application for the stable equilibrium condition. Got it? So you can note down this. So now based on this understanding, how can we state neutral equilibrium? So we have discussed what is stable equilibrium, what is unstable equilibrium. But there is a third case, neutral equilibrium. Neutral equilibrium. So in the case of neutral equilibrium, right? So in the previous cases, whatever we have discussed, if you give a little displacement, there are two things that are happening. Whether it can go further, which makes the unstable equilibrium, or it will come back to its original position, which will make the stable equilibrium. But if it tries to stay there itself, then that is the neutral equilibrium. That means, suppose if you give a little displacement, if it tries to get the equilibrium there itself where it was, the new position is occupied, and that is called the neutral equilibrium. That means, suppose if I have a table like this, on top of that there is a wooden block like this. Now I have given a little displacement to this block. So let us say it is moved to this new location. So here also stable, and here also it is stable. So in both the cases actually it is under the equilibrium condition, because the weight is always acted downwards like this, and even the weight here also the acted downwards, and the normal reaction is upwards. So here also both forces are getting balanced out, and here also the forces are getting balanced out. Even though if you have given a little displacement, so it is not coming back or it is not moving further. Hence this is called the neutral equilibrium. So giving a little displacement to the body if it occupies new position again with the equilibrium of forces, then the equilibrium is called as neutral equilibrium. Got it? Yeah, you can note down. Okay. Now, for a system of forces, how do we test the stability of equilibrium? So, are there any methods that are available for us? Right? So, there are three different methods that we are going to adopt. So, that is, one is the work function test. And another one is the potential energy test. And the third one is jet test. So these are the three different methods that we are going to adapt to find out the stability of the equilibrium of system of forces. Now, before understanding this, right, so we need to understand what is work function. So the work function is nothing but, suppose if there is a body like this, and on this body, if you apply a force like this, then this is going to make a displacement like this. And then if you put it on the coordinate axis, let us say this is the coordinate axis, this is x axis, this is y axis, and this is z axis. So if you put it on the coordinate axis, the analysis will be much more systematic. So this location, which is the center of gravity, let us say x1, y1 and z1 is the point. Now, so let us say this is the initial position vector. Now this is moved to a different location like this. Now this is the center of gravity whose location is x2, y2 and z2. So this is the new position vector. So this is R1 and this is R2. Now in between, so there is a displacement actually that got acquired by this because of the application of this particular force. Now this force, so though we have drawn in the form of parallel to the x-axis, it might be in any direction. So this is F can be treated as Fx into I plus Fy into J plus Fz into K. So this is a force I have applied on this particular body. Now it is moved to a new displacement. The initial displacement is, initial position is at R1 and the final position is at R2. That means if it is moved from here to here, then this displacement, this point is A and this point is B, then RAB, so you can calculate by applying the triangular law of vector addition. That is R1 plus RAB. So the sum of this vector and this vector should be equal to this vector. So this is R2, or RAB is equal to R2 minus R1. So R2 minus R1 is nothing but the displacement vector. So this is the displacement vector and this is the force vector. Now this displacement vector RAB, so for simplicity I call this as the vector R. So R can be treated as xi plus yj plus zk, like this. Actually if you put it, then dr can be treated as dx into I plus dy into j plus dz into k, right? So where this x is nothing but x2 minus x1, y is nothing but y2 minus y1, and z is nothing but z2 minus z1. So here actually this is the dr vector and this is a force vector. So work is nothing but, work is equal to force multiplied by dr vector, so which is a dot product between these two vectors. So this dot product Fx into I plus Fy into j plus Fz into k dot dx into I plus dy into j plus dz into k. So the dot product of these two is going to be Fx dx plus Fy dy plus Fz dz. So this is nothing but the elementary work done. So So if you move your displacement of dr, this is the work done. Now if you integrate on either sides, then this is going to be work is equal to from the initial position x0 comma y0 comma z0 to the final position x1. So this is x1, y1 and z1. This is x2, y2 and z2 is the final position for the work function f of x dx plus fy dy plus fz dz. And this is what is called the work function. So this is called as the work function. Got it? You can note down this work function. Now I will go a little deeper into this work function. Right? So work function is nothing but actually the work done. So the mathematical view of the work done calculation is nothing but the work function. Now here actually whenever there is a positive displacement that got contributed by a force, then actually the positive work is done by the force. Suppose if it is the other way, that means actually the force direction is different and the displacement direction is opposite to it. Then actually we say that the negative work done by the force, right? So that means suppose if this is the body and the application of this particular force actually it will try to move the body in the forward direction. So this is called the positive work done. Right? So here actually I would like to explain the conservative force field. So conservative force field meaning, suppose the work actually if it is expressed as an exact differential, if the work is expressed as an exact differential, then the force is called as conservative force. So this conservative concept, right? So conservative, what it means for us is, so it depends only on the position. So it won't depend upon the direction of the movement. So that's what is called the conservative force field. Now here actually there is a concept called field. So till now whatever we have dealt in the case of statics, right? So this is completely the finite forces what we are going to deal with. But suppose if there is something called field, field is a different concept that we are going to discuss in detail in case of fluid dynamics. So try to understand what is a field. Field meaning there are infinite lines of forces that are there in that particular direction. That's what it meant by field. For example, if you take the gravitational field, I mean here actually if I ask you to draw the direction of the force in case of gravitation, right? So there is no specific point of application there. Suppose if I take this chalk piece, if I leave it here, then actually it will go and fall down on the ground. Suppose if I move to Bangalore and there actually if I drop the chalk piece again, it is moving downwards. If I go to Delhi and then actually drop the chalk piece again, it is going down to the exactly in the same direction towards the ground. Now actually where is the point of application of this force? So everywhere this is there, right? So wherever you go, like even if you go to USA also, there also it will fall down towards the ground itself. That means where can you define the point of application of this force? You cannot. So that is infinite different lines of forces actually you can draw there. So this kind of scenario is called as the force field. So field is nothing but the same phenomena across everywhere. That's what is called the field. So this kind of field concept actually is very much useful in case of engineering. For example, if you take electric field, so in case of electric field, so there are different kinds of fields actually that we are going to deal with. That is specifically for us actually the fluid field what we are going to deal with. For electrical engineers actually they are going to deal with electric field and magnetic field. And even mechanical engineering also we are going to deal with heat field. So heat also actually a form of force field actually it will continue. So here this electric field, if I take a charge here, then if I keep one more charge, of magnitude plus q again, then actually there will be a line of force between these two. Now here, if I move this charge from here to here, again actually there will be a force like this. If I move this charge here, then actually again there will be a force like this. Now wherever you keep this particular charge, you will be noticing a force in that particular direction. That means if I take this as a unit charge, then the force on the unit charge we call as the electric field. What it means for us is, imagine that there is a unit charge that got placed everywhere. Then actually you will be able to draw a force line towards that direction. So in all the directions actually you can imagine that. So there is a force field. Now in this particular case, if you notice, earlier actually we have calculated the work. Now for this kind of scenario, how do we calculate the work? Understood? So if there is a single force that got applied on your body, then actually you know the force magnitude and you know the point of application of the force, you know the displacement of the body. Now here in this case, there is no specific force. So if I keep a charged particle here, there will be a force here. If I keep a charged particle here, actually it is force in this particular direction. Now everywhere actually the influence is getting there. Suppose if I keep one more charge here and one charge here, there will be a force on this particular direction as well. Right? So that means actually no specific force actually you can consider. So here actually all the forces together we call something called the field. So we are going to deal with only the conservative fields. So conservative fields meaning, suppose if I see this, there is a point charge here and the force lines are everywhere outwards like this, and then if there is a charged particle here, there will be a force. Suppose if I take a circle of radius same, then actually everywhere I place this particular charged particle will be affected by the same magnitude of the force, right? Same magnitude of the force, and it will always try to move away from there. Move away from there. Now actually work done by moving a charged particle till this particular location is nothing but the potential energy at this particular point. Now the relation between the potential energy and the work is nothing but, so as per the work energy theorem in physics, so whatever the work you do, that will be stored in the form of energy, because you are doing the work against a force, against a restoring force. So in such cases the work and energy are one and the same. Now actually the potential at this particular point is nothing but, if I take a charged particle from here and then bring to this location, so in bringing this charged particle here, I need to oppose the force that got exerted by this particular charged particle, because this is plus q magnitude and this is also a plus q magnitude. And then if I try to bring towards this direction, it will try to push away. Now actually I need to apply an external force with my hand to move from there to here. So in moving from here to here, I have done some work. I have done some work. So this work, whatever I have done, we call that as the potential at this particular point. Right? Now here, the importance of conservative force field, here it comes. Suppose actually, if I bring the same charged particle in this particular direction, should I be doing more work or the less work or the same work? I have taken a different path and traveled a long distance and then still coming back to the same position. Now, this path versus this path, should I be doing the same work or more or less? Any other answer? So, it will be the same work. Why? Because, see this, suppose I have taken, so I will give a different example. Let us say there is a force like this. So this is the force field. And I have taken a path like this, and then I have moved this charged particle from here to here under the influence of this force. Like this. Now this is point A. and this is point B. So essentially from A to B I have traveled in the direction of the force. Now what happens is, when I am moving in this direction, it will try to push the charged particle, or it will aid my force, right? When I am trying to move in this direction, this force also will try to move in the same direction. But when I come back here, if I am trying to move in this direction, it will try to push away, right? Now, whatever the component of the force that got aided in this particular duration in moving this direction, the same force is getting opposed in this direction. That means essentially from here to here is the effect. From here to here what happens is, till this point it is aiding, and till this point it is opposing. This is the aiding and this is opposing. So whatever it got aided here, the same thing got opposed, and finally these two are balanced out, and then essentially what is left over is, in moving the component from here to here, which is nothing but in this direction, the horizontal component is the force actually what we are requiring. So this is nothing but this component only, the essential useful part of it, correct or not? So whatever, now actually I take one more path. Now actually I move in this direction like this. Even here also, here it will aid, and by the time I come back actually it will be opposing. Now even here also, moving from here to here it will get affected, but this one is compensated each other. So finally whatever the path I take it, whether I have taken this path or whether I have taken this path, essentially I have done the work from moving here to here. Maybe a positive work or maybe a negative work. Positive work, I mean, if I move against the force, then actually it is the positive work. If I move along the force, that means it is aiding my force. That means I have done negative work. That means it is aiding. Suppose actually if you take the example, so going down to the staircase, then actually the potential energy is getting aided, so that actually we can go easily. But actually when I come back to the top of the stairs, then actually I should be applying more force, so that actually I can do some work and then come to the top position, right? So here also this is aiding work. Aiding work means I have done negative work, or it is helping me in moving from here to here. Suppose if I move from here to here, it is opposing work. That means I have to do certain work to move the particle. So here if you notice, whatever the path actually you have taken, it doesn't matter. The initial position where you started versus the final position where you landed is important for us. That too in the direction of the force, right? So here this kind of nature, for whatever may be the force it is having it, then that kind of force we call as the conservative force field. Got it or not? So it depends on only the position. It doesn't matter whatever the path you have taken. So even here also, whether you take this direction or whether you take this direction, finally you will be ending up doing the same work, because these force lines actually in some places actually it will aid, and in some places actually it will oppose that, right? So all these force lines whatever I have drawn, so at some place actually it is aiding and at some place it will oppose. Finally all those things are compensated, and finally in moving from here to here in a straightforward path, whatever the work you have done, the same work actually will be done whatever may be the path you have taken. But only difference is, in some places the force is getting aided and some places actually it is opposing. So that help whatever it has done, that it will take away finally. So essentially whatever the work you have done from here to here in a straightforward path, the same work has to be done in all the ways. Got it? So these kind of scenarios are applicable only for the conservative force fields. But luckily whatever the forces we are going to deal with are only the conservative force fields. We don't go into the complex level of force fields. So whether it is electric fields or magnetic fields or fluid fields, we are going to deal with only the conservative force fields. So in case of conservative force fields, I am going to deal in detail so when I deal with the vector calculus there. So if del cross F is equal to 0, then F can be expressed as minus del phi. So this is what actually we learn in case of vector calculus. So if del cross F equal to 0, then so F can be expressed as minus del phi, because del cross del phi is equal to 0, right? So here phi is a scalar function. So phi is a scalar function. This scalar function is having the advantage of depending upon the position of the particle. It doesn't matter whatever that path actually you have taken for calculating this phi. and this is what is called the potential function for us, right? So this potential function is constant or is dependent on only the position, but not on the path it has taken while moving the particle from there to here. So this is applicable only for the conservative force fields. Got it? So whatever we have learned in case of statics is only the finite number of forces where you know that what is the magnitude of the force and what is the point of application of the force and what is the direction of the force. But in case of force fields, what happens is there are infinite number of forces that are coming, but every force is having a magnitude and every force is having their own direction and every force is having their own point of application. So while dealing that, we are going to rigorously use the vector calculus there. So here, in case of del cross F equal to 0, del cross F equal to 0, we mean no rotational components. So what is meant by rotational components here? So in both the cases, whatever I have taken, if you notice, I have taken the forces only along the horizontal direction. Or actually, all the forces are parallel to each other. If I take Cartesian coordinate system, then actually, this is what actually it will make us del cross F equal to 0 because no rotational components are there for these forces, right? So no crisscrosses you can notice. Even here also, if I take the polar coordinate system or actually cylindrical coordinate system, if I take it, or the spherical coordinate system, if I take it, the force lines are actually moving radially away. No crisscrosses are there again. So if you take the cross or del cross F for this, so del cross F actually if you calculate for this, even for this also in polar coordinate system you are going to end up with 0. And where del cross F equal to 0 we call as the conservative force field because no crisscross forces are there, right? So as no crisscross forces are there, obviously del cross F will be 0, no rotational component, and F can ideally be equated to F is equal to minus del phi, where this phi is a new scalar variable that we have introduced now. So this scalar variable, whatever we have introduced, this is dependent on only the position, not the path it has taken while moving the particle from one location to another location. Now here, there is one more important aspect I am going to discuss it here. That is, this scalar function, whatever we have taken. Now actually, if you take the electrical engineering, right, we are always talking about something called potential or like voltage. So this voltage, we are talking regularly voltage. So the concept of voltage is coming from the simple reason of del cross F equal to 0, F can be expressed as minus del V. So just because of this single line, the voltage got utmost importance in electrical engineering. So why it is so important for us is, when we are dealing with the vectors, we always have to worry about three different components, X component, Y component and Z components. But for a scalar, you don't need to worry about the three components because it is a simple straightforward function, right? So we can do calculations with the scalars very, very easily because we are very well aware of the scalars. But in case of vectors, complicated mathematics actually it is going to coming into picture because every component needs three different components. And the multiplication of 3 actually will be multiplied to 9 times. So that's why the multiplication, division, addition, everything actually, it will be much more complicated when you are dealing with the vectors. So just by taking the advantage of del cross F equal to 0 for electric field, we were able to define something called phi, which is a scalar value. In electrical engineering terminology, we call this as the potential, electric potential or the voltage. And this voltage actually you can straight away add it as if like the straightforward scalar values, right? So this is how actually we have introduced the potential because electric field is a conservative force field. Got it? So here, little extension to our discussion is, in statics actually we are going to deal with only the finite forces where you know everything about the forces. But coming to the force fields, there is no specific definition. So because the influence is there everywhere. Now for dealing with them, you have to introduce the concept of vector calculus there. Got it? So this here, so the whole discussion, whatever we have done here, why? Because see this, there is something called work function test and the potential energy test. Now these two are interrelated to each other. Here, whatever the work we have done from here to here, the same thing is getting stored in the form of energy at this particular location. Why we call this as energy at this particular location is, if I remove my hand after moving, this will automatically push. It will go away from there because it has got that ability, because I moved this particle from here to here by using my own force. I have done some work. So this work is stored in the form of energy. The same energy it will be releasing, so that it will be going back and finally staying there. Where it will stay, that is one important question. So it will stay where there is the least potential energy. This is very, very important understanding. So if you move to this location, so where least potential energy is there. So where there is the least potential energy, it will try to stay there. Suppose actually if I take this chalk piece, now actually this chalk piece is on my hand now. Why? Because for this chalk piece, there is no other choice. It can get the least potential energy only on my hand now. Suppose if I leave it like this, then actually when compared to the ground, it knows that actually it has got more potential energy. So when it goes down and then stays on the ground, then actually it has got the least potential energy, hence it will stay there. So it will always tries to search for the least potential energy, right? So when there is a least potential energy, it is going to stop there. Now that important understanding of the least potential energy concept is applicable even for our this stability of equilibrium. So the equilibrium is under stable if the potential energy by all the forces together is coming out to be least. Now exactly the work function, exactly the work and potential energy theory, what it says is whatever the work you do, that will be stored in the form of energy. Now if it is the least potential energy, then you might have done the maximum work on that. It is one opposite to the other, right? One is the positive value and another is the negative value. So more work and less potential energy. So these two are interrelated. So the equilibrium is under stable condition under maximum work function or least potential energy. So these are the two important understandings. So maximum potential energy, so maximum work function or the least potential energy, where a body if it acquires, then actually the stability under equilibrium condition. Otherwise it is under the non-equilibrium condition or the unstable equilibrium condition, it will be there, right? You note down this, then mathematically we will prove this, why it is stable and why it is not stable. So this work function test is, now actually as the system is under equilibrium condition, initially, then the principle of virtual work can be applied. So if you apply the principle of virtual work, then dW is equal to 0, where W is equal to from initial position to the final position x1, y1, z1 fx dx plus fy dy plus fz dz. So this is the work function. Now this work function, it says that dW is equal to 0. So for any variable, if I take it, y may be a function of x, y, z. If I take the derivative of that function, actually it is coming out to be 0. So as the derivative is 0, initially then the work may be maximum or minimum. Right? So because the derivative is 0, obviously the derivative, if it is 0, then the only possibility is the work can be maximum or minimum. So whenever we find out the maximum value or the minimum value for any random function, right? So we will try to do the derivative first and then equate to 0, and then try to identify the stationary points there, and then find out the second derivative, and then try to verify whether it is the maximum or minimum. That means in all the cases, first you will be verifying whether the derivative is 0. Here actually for a stable equilibrium, for an equilibrium condition, whether it is stable or not, it doesn't matter. But the work function may be definitely either it may be having a maximum value or the minimum value under the equilibrium condition, right? Because dW is equal to 0 as per the principle of virtual work. Now here, so if dW equal to 0, then so we take two different cases now. Here, suppose there is a ball like this in a bowl. So there is a ball in a bowl. Now actually I have moved this ball to this location. Then actually it will try to come back. Now here, if you notice, here actually we will take two different conditions. Let us say one case is maximum work function. And the second case is minimum work function, because both are possible. Now let us say if it is having a maximum work function at this particular location, then if you apply an external force to move this direction, right? So if it is maximum work function, so this is W and this is W dash, which is the new work function at this location. So this is the initial work function. So after moving this location, because it has got the new position, it will be having one more work function, W dash. Now if it is maximum at this location, obviously W dash is less than W, right? Correct or not? W dash is definitely less than 1. So if you take case 1, so work is actually more at this particular location. So if you try to move this location up, then actually what happens is that external force, whatever you have done, it will always tries to bring back to the original position. Now in this case, if W dash is maximum at this location, obviously W dash will be less. If W dash will be less, then actually it will try to bring the force down, so that it will have the maximum work function at this location. That means as and when if there is a maximum work function, it will bring back to the original position. Hence this is under stable equilibrium. Suppose if I take the other way, suppose this is the minimum work function. If it is minimum work function, then actually it will be this kind of scenario, wherein this ball is like this. So here minimum work function. If it is minimum, if you give a little displacement, it will fall down like this. So here actually W here and W dash here, W is less than W dash. If W is less than W dash, then actually if you give a little force, this force will do a positive work and then actually it will try to move away from there. So as and when there is a positive work, positive force, as and when actually if you apply a force, if it is moved further, then actually we say that that is a positive work done by the force. Suppose if it is moved back, then actually negative work done by this. So if W dash is less than W, then actually so W minus W dash will be greater than 0, obviously. This is the positive work. In this particular case, what happens is W minus W dash is less than 0. So this is W minus W dash is less than 0, negative work. And this is positive work. So suppose actually if I take a body like this, on this body actually if I apply a force, there will be a definitely associated displacement. Now in this case actually we say that work was done, right? Because this force is moving this body in this direction. That means there is a positive work. Right? So there is a positive work. Now actually positive work actually if it is moving this direction, now here this is a positive work. Positive work actually, so the force whatever you apply, right, it is coming back. Hence, actually, W minus W dash is greater than 0, which is a positive work. But here, it is the negative work. W minus W dash is less than 0. So, negative work means, so work energy is getting released. Hence, actually, we got the negative work. So, as I said, right, to lift this chalk piece, actually, I have done some positive work. But if it is going down, so it is aiding my hand, right? So, it is trying to push down. That means, this chalk piece is doing work on my hand. Earlier, actually, I have done work on this chalk piece to move to the upwards. This is the positive work. If it is moving back, this is the negative work. Got it? So, based on this understanding, if W minus W dash is greater than 0, which is a positive work, then actually the stability under equilibrium condition. Suppose if W minus W dash is less than 0, this is under unstable equilibrium condition where we have the negative work. That means from these two scenarios, we can conclude that if W is maximum work function, then it is stable. Otherwise, it is unstable. Got it? I hope it is understood. Fine. So you can note down this. Note it down. Now here actually, the second case actually, the potential energy test actually we can analyze from here itself. Now if you notice, in both the scenarios, this is having the more potential energy or this is having the more potential energy. So this is the first one and this is the second one. Which one is having a more potential energy in both of these? So second one is having a more potential energy. First one is having the least potential energy. Obviously, as I said earlier, wherever there is a least potential energy, it will try to go and stay there. So that's why this is under a stable equilibrium condition. This is under unstable equilibrium condition, obviously. So that is the second test, which is nothing but the potential energy test. So when the work function is maximum, there the potential energy is minimum. As I said, work energy theorem says that whatever the work you do, it will be stored in the form of energy. That means if you do the more work and the more energy is getting stored. But actually, the stability will be coming only under the least potential energy case. That means work and potential energy are opposite to each other, right? So here, if it is having maximum work function, then actually it is under the least potential energy. See, this is having the minimum work function, but maximum potential energy. So wherever there is the least potential energy and maximum work function, the system is under equilibrium condition. And wherever there is least work function and the maximum potential energy, where the system is under equilibrium, under unstable equilibrium condition. Got it? So these two are the important tests. So that is the work function test and the potential energy test. Now the third one what we are going to deal with is, that is the jet test. Jet test is specifically for the, when there is only the gravitational force that is there on the body, then actually we go for the jet test. First you note down this. So I think so I will continue the class tomorrow. So there is only one important derivation in this stability of equilibrium. So that is a little complicated derivation. I will elaborately explain each and every aspect in a completely one session. So based on that formula, whatever we are going to derive, so all the problems can be solved, right? So in the next class actually, so that is derived from the jet test itself. So tomorrow I will take jet test along with the derivation for the conditions for the equilibrium. Got it? Stable equilibrium condition. So do you have any questions on this today's class? Any questions? So that's all for today. So in the next class, I'm going to deal with jet test and the conditions for the stable equilibrium.